Okay, so higher level section for this atomic theory unit, looking at the electrons in atoms. And this is what we're looking to do by the end of the section: understand what the convergence limit is, look at ionization trends and patterns, and use successive ionization energy data to identify elements. So we'll start by looking at what a convergence limit is. And if we look at these energy levels up here, as we get further away from the nucleus, it's working again, there we go. As we get further away from the nucleus, so there's our first energy level, second energy level, third, fourth, fifth, sixth, seventh. You can see that things are getting gradually closer and closer together. And that's going to be mirrored in one of our line spectra, in our series of lines. You can see that the lines for the transitions get closer and closer together as these energy differences here get smaller and smaller. And eventually there comes a point where these energy levels, there's no difference between them. And that's going to cause these lines here as well to converge. And at that point the electron has been lost, it's been ionized. So if we're dealing with hydrogen, which is 1s1, our electron lives normally, ground state, in the first energy level. And as a result we'd be looking at this series of transitions to decide where our convergence limit is and to work out an ionization energy, which is what we're going to do on the next slide. Here we are. So here's our emission spectrum, and there's our convergence limit. You can see the lines getting closer and closer together. There they've converged, and it's actually written on there what the value is. I can't quite see it. Let's say that it's something like 910. And that's 910 angstroms. Now an angstrom is 1 times 10 to the minus 10 meters. So that's our wavelength. And we're going to use this relationship here to convert it to a frequency, which we're then going to use to work out an energy. Right, so we'll take this and we're going to use our relationship C equals frequency times wavelength. And our speed of electromagnetic radiation is 3 times 10 to the 8. We don't know V. Lambda we've got here, so I won't write that out again, that can go in there. And if I solve that for the frequency, I'm getting a frequency of, guess again, there it is, 3.2, oh dear, hold on, running out of space, 3.30 times 10 to the 15 per second. Now I'm going to put this into this equation, and I'm going to multiply that by Planck's constant, which is listed here as 6.63 times 10 to the minus 34. And that's going to give me the energy times 6.63. So that's coming out to be 2.19 times 10 to the minus 18. And that's kind of, I guess, for sort of one transition. It's more sensible to think in terms of moles, right, for a mole. And within 1 mole, we've got 6 times 10 to the 23 hydrogen atoms. So I'm going to scale that up by multiplying it by that number, 6.02 times 10 to the 23. You'll be working more with that number in the next unit. But if I do that, it's going to give me my final answer in joules, so times 6.02 times 10 to the 23, which is, so there we go, 13158, what a mess, sorry, joules, and converting that to kilojoules, dividing by 1000, I'm going to write it as 1316, let's say, kilojoules per mole. Right, so from this convergence limit I've been able to work out the ionization energy. My apologies for the very scrappy working on there. Right, so we've talked about this trend in first ionization energies before, I think, in the standard level section. Two key areas to look at here and here. We've got a general upwards trend because we're adding electrons to the same energy level, but all the time there's more protons in the nucleus. But what we're finding here, for magnesium going to aluminium, so we're starting the P sublevel, and we've got a very slight drop as we go from an S1, S2 to a P. And then here, if we think of Hund's rule, this is P1, that's P2, that's P3, that's P4. Now we remember that in our terms of our electrons in boxes, the electrons exist singly before they start pairing. And it's here that we start getting them pairing up, two electrons in the same orbital, tiny bit more repulsion because they're both negatively charged, and as a result there's a very slight drop there. If we take successive ionization energies, so if we just keep plucking the electrons off of an atom, it gives us a clue as to electron arrangements and how many are in each energy level. So this one here, which is 281, right? So, oh, my apologies. Yeah, 281 is the electron configuration there. What we've got is one outer electron that comes off relatively easily. You can see it's low energy. That's this one. Then we've got the next shell, the next energy level, which is containing 8. And then the two that are hardest to get off are the ones closest to the nucleus. And so we've got 2 there like that. And you can see this one over here, there's 4 that come off relatively easily, so there must be 4 in the outer shell. And then there's 2 in the inner one, so that would be carbon. This one here, you've got 1, 2, 3, 4, 5, 6 that are coming off. And then there's a jump to those 8, and then there's 2 on the inner shell. Right, so that must be oxygen. So we can look at these and we can work out which atom is which. Good, so that's what we've covered. There's a list of resources that I borrowed. Thank you very much.